Hi everyone, welcome to our session. Today, myself and Kanchan are going to talk about xNVMe BDEV and its building blocks. This path has recently made its way into mainline SPDK and Linux kernel. Here is the outline of the talk. First, I cover the SPDK basics and the problem statement in hand. Then Kanchan is going to talk about the new in-kernel pass-through path. Thereafter, I will elaborate on how we use this new pass-through to build a new BDEV in SPDK. In the end, we show the performance data using this BDEV. SPDK is mainly used in enterprise, and there are a lot of SPDK applications that work in the enterprise environment. Enterprises are migrating towards cloud infra. In the cloud environments, the NVMe devices may be abstracted and may be virtualized. As we know, to use the NVMe devices with the SPDK applications, first they need to be detached from the OS NVMe driver and then attach it to the drivers such as UIO or VFIO so that SPDK can use the devices. In the cloud environments, if the NVMe devices cannot be detached from the kernel NVMe driver, SPDK applications may not be able to use them. We propose a solution to this problem by implementation of xNVMe BDEV module and using its IO using command asynchronous interface so that the underlying NVMe devices can be used by the SPDK applications. So the SPDK applications that are transitioning to the cloud environments are the main beneficiaries of this feature. Now that we have got a fair idea of the problem statement that we have in hand, let's deep dive into what is SPDK and the internals of it. SPDK stands for Storage Platform Development Kit. It is a collection of tools and libraries that are entirely in the user space. It is an open-sourced BSD licensed software primarily developed by Intel. SPDK enables the developers to write high-performance, scalable user space storage applications. Why do we need SPDK? There is a shift in the storage industry from the slow spinning disks to fast solid state media. As the media is getting faster and faster, the software stack latency has become a very big bottleneck. To overcome this, the software latency should be minimized as much as possible to take advantage of the underlying fast media. SPDK does this job perfectly by minimizing the software latency and increasing the performance. How does SPDK achieve low latency and high performance? It is by use of the following three methodologies. Firstly, it is entirely in the user space. Kernel acts as a middleman between the applications and the underlying hardware, which is quite burdensome. SPDK removes this middleman entirely and provides an incredibly efficient access by connecting the storage applications and the hardware. Secondly, SPDK has a lockless design. This design gets out all the inherent parallelism present in the media. Lastly, it is a polled mode driver model. It does not rely on the interrupts on the underlying hardware. Rather, it keeps polling to fetch the IO completions from the hardware. Where do we find SPDK? SPDK source code is available at the GitHub location mentioned here. The community discussions, submission of patches to the community, articles about SPDK are available at spdk.io. This figure showcases the architecture of SPDK. As mentioned earlier, SPDK is a collection of tools and libraries in the user space. SPDK has been integrated with various storage applications such as RocksDB, Ceph, and it can support various CLI and benchmarking tools such as FIO, NVMe CLI, etc. SPDK supports block layer stacks similar to that of any operating system in the user space. It has support for the file system referred to as blobfs, and it communicates with the blob store. SPDK has support for NVMe driver that supports PCI, RDMA, and TCP transports. The NVMe driver is the bedrock of the SPDK storage stack. It is a polled mode driver. Let's dive into the details about the block device layer. It supports two types of APIs. One is the pluggable module API and other is the application API. Application API provides a generic API interface to perform IO operations such as read and write on the variety of block devices. It also supports in claiming and enumeration of the SPDK block devices. Pluggable module API, on the other hand, helps in the implementation of the block devices. It unifies the interface between different kinds of storage devices. The following are the features of the block device layer in the SPDK storage stack. Queuing of the IO requests, timeout and reset handling, logical volume management, and partitioning of the block devices are some of the features. It supports multiple lockless queues to perform I/O. Configuration of the block device can be done via the JSON RPCs. Applications can perform the block device operations over the block device layer or file operations over the blob-FS. The block and file operations are further submitted to the underlying SPDK drivers or to the Linux IO stack depending on the type of the block devices. The block device layer is divided into two parts. One is the block device abstraction layer and other is the block device modules. The abstraction layer provides a consistent API for various types of block devices. APIs can be invoked directly by the SPDK applications. Coming to the BDEV modules, they are user space libraries that implement various types of block devices such as NVMe, AIO, etc. The IO requests are sent on the individual block devices. The block devices are hereafter referred to as BDEVs. They are of two types, base BDEVs and virtual BDEVs. Base BDEVs handle the IO requests directly, whereas the virtual BDEVs handle the IO requests by routing them to other BDEVs. Let's discuss more about the internals of the BDEV modules. The modules have to be registered first with the SPDK and later on the BDEVs are created within these modules. Registration of the BDEV module happens with the invocation of the module register macro by passing a pointer to the SPDK BDEV module structure as an argument. The SPDK BDEV module structure consists of different function pointers that needs to be implemented by the BDEV module. After the BDEV module is registered with the SPDK, the individual BDEVs can be created within the module by invocation of the SPDK BDEV register function by passing SPDK BDEV structure as an argument to it. The SPDK BDEV structure consists of a SPDK BDEV function table that consists of various function pointers which are to be implemented by the BDEV module so that the IO operations can be performed on the individual BDEVs. This slide showcases how a BDEV module can be registered with the SPDK storage stack. Image on the left shows the SPDK BDEV module structure that contains various function pointers that need to be implemented by the BDEV module. Module init is a mandatory function pointer that needs to be implemented as it is the initialization function for the module. It is called by the BDEV library during the startup. Most of the other function pointers are not mandatory to be implemented by a BDEV module. Image on the right shows the sample code from the AIO BDEV module. The module is registered to the SPDK stack by calling the macro module register with the pointer to a SPDK BDEV module structure that is initialized with the function pointers. After the BDEV module is registered with the SPDK storage stack, the individual BDEVs can be created by calling the function SPDK BDEV register with a pointer to SPDK BDEV structure as an argument. The most important field of the SPDK BDEV structure is the SPDK BDEV function table. It consists of function pointers which are necessary to perform I/O on the individual BDEVs. Image on the left shows the SPDK BDEV function table structure that contains various function pointers that need to be implemented for the individual BDEV. Image on the right shows the sample code from the AIO BDEV module. With this, we have got a high-level understanding of the SPDK BDEVs. I will now hand over to Kanchan to talk about the new in-kernel pass-through.
Thank you, Krishna. So we get into why this new path is required and what it contains. If we look at the picture in the middle, NVMe driver exposes the block device interface for the underlying NVMe. In-kernel file system plays the FS abstraction over this block abstraction, but there are a couple of problems with this path. First is that the block device interface is subject to various constraints, and if those are not met, it fails to come up. This happens when NVMe device contains unsupported features or it exposes a new command set other than NVM and GNS. Regardless of this availability problem, there is this fact that NVMe is giving birth to newer ways of interacting with an underlying storage. Classical read-write that OS understands well is not enough. Application require new system call to consume, but new system calls are hard to grow because it takes time to fit into OS abstractions and also because it comes with maintenance baggage. IOCTL could be one way to drive such interfaces, but that defies the purpose of using NVMe because IOCTL is a blocking call, submission and completion are tied, and IOCTL is far from various other measures that improve the efficiency. We'll see some in the next slide. Coming to the new path, shown in the yellow colored box over here, it's based on /dev ng0 and 1. It's unconditional, always comes up even if device has got unsupported features or a new command set. Any admin or IO command can be sent in the same way, not just read and write. It cuts through abstraction, so new system calls are not required, allowing application to speak NVMe. And this is efficient as it is paired with IOring. Next slide explains more. So this path is a zero copy between user and kernel. During submission, kernel doesn't copy from user, as the command is placed inside the SP, which is the shared memory. And completion also happens via the shared CPU memory, so no put user overhead. The second is that there are no allocation in the IO path, both in the user side as well as in kernel. Big SP of the IOring gives 80 bytes of free space that application can use, and kernel uses the pre-allocated memory for any bookkeeping that requires for asynchronous processing. The right-hand side table shows other knobs to improve the efficiency: vectored buffer, submission polling, completion polling. All these are possible with this new path. Now, here is example of doing I using this path. First thing first, application need to open the generic CAD device, and then it asks IUring to set up big SQE and big CQE. Then it fills the opcode, which is URING command inside the SQE. And after that, it goes about filling the NVMe opcode into it. This application uses URING command IO as a opcode, but if it wants to send multiple buffers, it can use URING command IO vec instead. And if it wants to send admin command, there are opcodes like URING command admin and URING command admin vec as well. And then it's going to extract the command from SQE. It doesn't have to allocate, as I said before. Populate this particular command with NVMe specific fields and submit the SQE. Later point of time, it can read the completion and can get both primary as well as the auxiliary result from the CQE. Now, if you look at the upstream status, the generic device interface is available since 5.13 kernel. And from 5.20, it will support any new or non-existent NVM command set. And URING pass-through for both admin and IO command is available from 5.19. Now I will pass the control back to Krishna for rest of the talk. Thank you.
Thank you, Kanchan. Now I will explain how the xNVMe is modified to support the pass-through functionality and how it enables the applications to use this feature. Before we jump into the details, let's talk about what is xNVMe and where is it available. It is a user space library that provides cross-platform abstraction and an unified API primarily for the NVMe devices. It enables user space storage applications to interact with the NVMe devices using a wide variety of interfaces. It supports multiple backends such as Linux, Windows, SPDK, and it also supports synchronous and asynchronous interfaces. The storage applications need not customize their code specifically for the interfaces such as libIO or IOUring. They can just develop their code using the xNVMe APIs and seamlessly switch the backends and the interfaces without worrying about customizing the software specifically for the underlying backends or interfaces. xNVMe source code is available at the below GitHub location. The articles, conference presentations about xNVMe, and the necessary documentation are present in the xnvme.io site. I request you to go through these links to get a more detailed understanding about xNVMe. Now let's dive into the details about how the pass-through feature is supported in xNVMe. As discussed earlier, xNVMe supports multiple backends and a variety of synchronous and asynchronous interfaces. libIO, IOUring are some of the asynchronous interfaces supported. In addition to these, IOUring command asynchronous interface has been implemented. The source code for this interface is present in the following file. This interface uses the pass-through functionality supported by the Linux kernel. This interface submits NVMe pass-through commands through the IOUring interface and reads the completions for the submitted commands. This feature is available from the 0.3.0 release of xNVMe present in the below GitHub location. These images showcase how a sample application can perform write operation on the NVMe device using the Linux backend and with the libIO and IOUring asynchronous interfaces. As you can see, the interface can be seamlessly changed by just modifying the parameter async from libIO to IO earring, whereas all the other parameters remain the same. This image showcases how the sample application performs write operation using the IO earring command pass-through interface. The interface can be selected by passing the value IO earring command to the parameter async and by selecting the generic NVMe character device instead of the regular NVMe namespace block device, whereas all the other parameters remain the same. The generic storage benchmarking application FIO can perform IO using the pass-through interface by using the xNVMe IO engine. It has been implemented and it is now a part of the upstream FIO. To use the xNVMe IO engine with the FIO, the parameter IO engine has to be specified as xNVMe. The synchronous or asynchronous interface needs to be specified with the parameters xNVMe sync or xNVMe async. The pass-through interface can be selected by passing the value IO earring command to the parameter xNVMe async. By modifying the parameter values, the interfaces can be seamlessly switched among libIO, IO earring, or IO earring command based on the requirements. The below link has a detailed write-up on how to use the xNVMe IO engine with the FIO application. Let's discuss about how to enable SPDK applications to use this feature. The xNVMe BDEV module is implemented alongside the AIO IO earring BDEV modules inside the block device layer of SPDK. By selecting appropriately, the IO can be performed through the libIO or IO earring command asynchronous interface of xNVMe. Code for the xNVMe BDEV module is present in the directory module BDEV xNVMe. As shown in the below images, the xNVMe BDEV module is registered using the SPDK BDEV module register macro. After the module is registered, the individual xNVMe BDEVs can be created and deleted using the remote procedure calls. xNVMe create and xNVMe delete are the RPCs for the creation and deletion of the xNVMe BDEVs. Options are passed through JSON configuration files. Name, file name, and IO mechanism are the options present as of now for the xNVMe BDEVs. IO mechanism option specifies which type of asynchronous interface to use. The following images show the sample JSON files. As you can observe, only the IO mechanism differs between the AIO and the IO earring JSON files. In the case of IO earring command, the file name also differs, so as to use the generic NVMe character device for the pass-through feature. This way, the underlying asynchronous interfaces to perform the IO can be seamlessly changed by just modifying the options in the configuration files. This slide explains the function calls that are invoked while creating the xNVMe BDEVs. The RPC xNVMe create invokes multiple functions to open a xNVMe handle for the device, to initialize an xNVMe IO queue for submitting IO commands, to register a callback that gets called for each command completion, to register a poller that keeps poking for xNVMe IO completions, to read the status of the command completion, and then to complete the IO. This slide explains how the IO happens on the block device layer of SPDK. xNVMe submit request function is invoked from the block device layer when the IO has to be performed on the underlying xNVMe block devices. It registers a callback that gets called after the allocation of memory required for the IO, and finally it invokes the xNVMe API command pass-v with a read or write specific operation and the necessary parameters for that operation. This slide explains the function calls that are invoked while deleting the xNVMe BDEVs. The RPC xNVMe delete invokes multiple functions to unregister the xNVMe BDEV and then to close the xNVMe handle for the device. xNVMe BDEV module is part of SPDK mainline now. To build SPDK with the xNVMe BDEV module, run the configure with the option with xNVMe and build the code with make. SPDK applications that use BDEVs can utilize the pass-through interface without any change to their interface. The next three slides showcase how the SPDK applications Hello BDEV, BDEV Perf, and FIO can use the pass-through interface using the xNVMe BDEV. These applications can just modify the parameter IO mechanism in the JSON file to seamlessly change the interface from libIO to IO earring or to IO earring command. This slide showcases the performance numbers that are captured with the SPDK xNVMe BDEV using the pass-through interface and compared with the performance numbers of the SPDK AIO BDEV. The workload details, system and device configuration are mentioned here. With this, I am going to wrap up our session, and we are very much thankful to SNIA SDC India for providing us an opportunity to explain about our work. Thank you very much.